Hi and welcome. In this talk, I'd like to share some details about the work that we've done recently to improve Magnolia performance. As you know, the complexity of Magnolia projects is growing year by year, and the system is constantly put to a new challenge. While we're evolving the architectural solution gradually and especially trying to fully unfurl the potential of Magnolia DX Cloud, we spotted quite a few opportunities to improve the existing DX core architecture and basically deliver the benefits that can be reached much sooner, allowing us to actually take time and focus on broader changes later. Um, so I'm your presenter today. I'm Alexander, lead architect and old-time Magnolian. Some or many of you may know me as Sasha. Performance. In this talk, we will briefly observe about what actually performance constitutes, what kind of issues and problems we have tackled, and what's been achieved, what tools we used, etc. And at the end, I hope there will be some time for questions. And when it comes to performance, it can be quite subjective. Some things are meant to be, some things are meant to take time and be relatively slow, but still be considered performant, like large imports and the publication of very large content sets and such. However, some are considered and expected to be snappy, such as UI operations or publishing of smaller content sets like individual pages and whatnot. However, a lot of things can go sideways. And for example, the instance may go low or, God forbid, out of memory, or CPU can spike or get too busy, or database communication can get too chatty and I/O becomes a bottleneck. Or simply, there's no big resource consumption, but too many threads are just waiting for some lock that is held by something else and are not produced in observable time. And basically, all of those problems can affect the overall system performance and slow things down, which we don't want. And that's something that we've been trying to improve over the past several months. And that's what we're going to be talking about today. So when it comes to Magnolia, there are some usual suspects, we'd say, and probably the most prominent one is unfortunately Jackrabbit. So as you know, we still use Jackrabbit 2, and its features like indexing and observation, especially if not used carefully and with consideration, can cause problems. And our more workforce modules such as publishing and versioning, in addition to heavy duty extensions and modules such as imaging or live copy, can suffer from that. And that's basically was our main area of investigation and improvements later. But how to deal with performance issues? And actually, while working and collaborating on some of the problems through support or during product development, I've observed that there's often temptation or tendency to start sort of digging into the code and start making conclusions just based on symptoms. And this often simply stalls the investigation or may even lead to the wrong conclusion and wrong path. So my take here is to kind of stay away from judging about performance without sufficient context and sufficient helper materials provided. And such materials could include logs, for example, in the worst case. However, heap dumps, spread dumps, or even better, execution profiles help much better and allow us to fix issues faster. And luckily, JVM provides various means and tools that help aggregate such artifacts, such materials. So I encourage everyone to do that. Even IntelliJ these days is equipped with a whole variety of tooling that helps quite a bit. However, let's take a look at the actual problem case that we've encountered some months ago with a partner reporting out-of-memory issues on a project involving publication of some heavy pages, 5 megabytes plus in size and such. And what was happening is the instance was running out of memory when a handful of such pages was attempted to be published. CPU is spiking. And it was pretty clear what to do and why is it happening, and especially what should we conclude. It was pretty tempting to just play the publishing mechanism, which definitely needs improvements, and probably, as you know from other talks and from panel discussions, that We have this new Swiss publishing initiative that comes soon and will tackle a lot of problems and will be more performant, hopefully. But as you can guess, like just blaming publishing was a bit premature conclusion, and there's been something we could do in the meantime. And to troubleshoot out-of-memory problems, what we really need and the most essential artifact is a heap dump, since it contains at least information about the objects that fill up the RAM, the heap, so we can start investigating. This is actually the first thing I personally ask when approached with Kinkers about performance problems, because otherwise we're sort of blind. And luckily in JDM, it's pretty easy to obtain a heap dump, because like with these two simple JVM keys provided on startup, if unfortunate situation happens and we run out of memory, then heap dump is provided out of the box, and we in Magnolia are very happy to take a look at it and solve the problem together. So let's say we've obtained a heap dump. Usually it's a very large file and a lot of information. So what tools do we use to analyze them? So a lot of engineers go with like a go-to tool, the Visual BM, which comes with pretty much any JDK distribution. However, a bit more advanced analyzers such as ones that come, for example, with commercial profilers such as JProfiler, may pay off in the long run, and in the following slides, we'll take a sneak peek why. So for this particular memory problem, I'd used JProfiler heap locker, and after waiting for a bit for it to parse the whole big heap dump, we instantly see that something is there that doesn't intuitively or at least directly relate to publishing. So the heap, which was 4 gigabytes max, was dominated by nothing but Jackrabbit observation events, which is already interesting. But what is more interesting was to know like why are there in RAM, what fault references, and why there's so many of those events. And that's where JProfiler actually comes very handy, since simple heap dump analyzers offer kind of the basic information on the object distribution in the heap and some trace referencing, reference tracing, but JProfiler can easily compute a collapsed or merge the references, allowing us to see where most of the event, in this particular case, most of the event objects are coming from, instead of like inspecting each individual event one by one. And there's like 82 million of them in this case, which would be tedious. Needless to say that JProfiler allows to also compute outgoing references if you want to see like or what other objects this particular one holds. But in this case, so we are more interested in the incoming references. And so in this particular case, when we select those events and expand them in JProfiler, we actually see that like eventually for this kind of stack of chained references, we see that most of them actually lead to flash listeners of cache module, which is not exactly what we did suspected initially, given the problem was triggered by publishing. And that's a good lead to start fixing the problem. And as you can see, heap dump in this case helped us start tracing the problem without even knowing the code that much or running everything, which saves a lot of time in investigation. And like, I mean, a little bit of fast forward, but eventually it turned out that there's indeed been quite a large amount of sites registered in the system, causing like excessive amount of JCR workspace observers. In this case, it was around 2,000 of them registered, and causing a problem with cache module. So in conclusion of this problem, like, okay, so there's been a large amount of large pages with a lot of nested components, megabytes in size, and when we publish a Ethereum, will trigger a lot of JCR updates and a lot of JCR internal observation events, for example, for reindexing, and then exacerbated by the large amount of sites in the system with on a lot of cache listeners and a lot of observers, leading to a lot of RAM being allocated and eventually plugging the whole suit. But my bottom line here is that what actually intuitively was related to publishing was actually caused by something different, and he not help us reveal that. In order to improve the situation, we actually introduced a new solution for flush policies that no longer rely on observation, effectively shedding all those 2000 problematic ones and basically unblocking the heat and eliminating the out-of-memory problem for this space. Here you can see an excerpt from release notes, and I encourage those interested to actually go through release notes of fast several minor releases in all Magnolia versions that have more details about like what has been done and what we have fixed. But in this case, so that was about cache flush policies, and also same release note mentions side quest from this same problems. So besides of just observing the big amount of event objects, we were wondering like why there's just so many event listeners altogether. So it spotted 2,000 related to cache, but otherwise there's been 7,000 in total, which is still a lot, like even like 5,000 remaining. And same technique, just tracing not the events, but event listeners now revealed that there's a lot of them that are allocated for powering the registries, the ones that bring definitions such as battles and templates. And we have concluded that actually we can collapse those into just several ones, and eventually rewrite from some thousands of JCR observers in the system to just several hundreds that we actually resulting to less garbage allocated and less memory consumed and optimized performance for larger pages, avoiding pitfalls with memory consumption. And for this particular case, eliminating the out-of-memory problems. And as a side effect, also leading to faster JCR configuration reloading. Don't want to dive too much in the code, but I just wanted to highlight how much AI helps sometimes. So besides of all this optimization for observers, we also noticed that events are just not processed fast enough. And I've been digging through a lot of our internal Magnolia code, because Magnolia has its own layer of observation on top of JCR and Python buffer the events. And AI actually helps spot the lock contention problem, because we've noticed that when we buffer events as they come from JCR, ironically, to actually improve performance a bit, we over-synchronize our own buffers, leading to events trial up without being processed while they could have been. And as a result, we've implemented the lock-free solution for event buffering in Magnolia, and so we'll no longer unnecessarily blow up or stall JCR observation threads, especially under stress. So that kind of improves Magnolia throughput when something heavy is going on in the background, and generally improve the processing speed of observation events coming from JCR. But we started this talk with a problem related to publishing, and now we return to it, because even with all those optimizations done to observation mechanism, publishing still causes issues and could be optimized. Well, we're finalizing the Suite Publishing Initiative, which, by the way, incorporates most of the problems that have expired like recently or even over the past couple of years. There's been a couple of things that we could have done in the meantime before Swift Publishing lands, and I would like to highlight some improvements that we have achieved. So basically, publishing is that slow, and we need to figure out why, and that's where actually CPU profiler comes in handy. And in the several polling slides, I'd like to highlight the usefulness of the tool called Flame Drops that helped us troubleshoot those issues. So you can see a screenshot of the flame graph taken from the internet. In this case, it represents the recording of MySQL query execution. But what is flame graph in a nutshell? It's basically a visual representation of stack traces that have been executed while you were recording your software execution with profiler turned on. And flame graphs are produced by many modern profilers, pretty much all of them, I guess, the latest versions, and they help trace all sorts of performance problems such as CPU, also memory allocations, locks, DD queries, etc. And something I wanted to highlight. They also, much like Sufams, help reason about the code that you aren't closely familiar with. And return to previous slide in this case. So how to comprehend plane graphs, how to read them. So basically, it's very easy. You can look at them vertically, and vertically, like all those bars that stacked on top of each other represent the same stack trace. So like functions or method calls, and then those subcalls that they make. And then horizontally, the width of the bars means how much this or that stack trace execution took relatively to other stack traces in the same graph. So you can see some of them are small, even like invisible, or very, very narrow, while some are very wide, meaning that these are the wide ones is ones that we want at Apple. And the performance engineer job is to make the bottom line bars as narrow as possible, meaning that the whole execution of the stack trace became cheaper and became faster. And we made some recordings of publishing operations on POS on some cloud instances, and probably it's a little bit small, but there's while most of the stack traces are narrow and invisible, there's some very, very wide on other instance right in the middle. And it actually is related again to JCR, and this time to the C index update. So it was rather unfortunate because publishing process doesn't really logically modify content that much. So why all the reindexing? And the question remains, what is going on? How can we optimize the process? So if we zoom in the flame graph and if we look closer, then we see that most of those index updates are triggered after we were done actually publishing. So all the content is sent to publics and being accepted. And then we do actually metadata updates, such as updating last published versions, status, and related metadata like who, when, etc. So to sum up, indexing update triggered by those metadata properties takes up to 50% of full CPU time on author during publication. And vast majority of those properties that are updated are not even the subjects but variants, so they shouldn't be even indexed in the first place. And the only wish is that if only Jackrabbit allowed to ignore or blacklist them. Because Jackrabbit actually, whenever you update something, it reindexes all the content. And with very heavy pages, especially that have a lot of components and a lot of content properties, this can become very expensive and very lengthy. So, in order to improve the solution, improve the situation, we have added some customizations to how Jackrabbit dispatches and detects the need for indexing in the first place, allowing for certain properties to be just skipped. So if like we do not expect, or maybe you in your project do not expect something to be actually used in queries, now there is this special configuration of index per workspace that allows to ignore certain properties, and unless some meaningful in air quotes properties are changed, no reindexing will be triggered whatsoever. So, and in this, it's an experimental feature still. So we're like carefully observing the consequences of this step. But it's possible to enable this with the feature flag that you see on the screen. And there's a link to documentation which describes the like how it's done in a bit more detail. So as a result of this optimization would significantly reduce the CPU and RAM stress on Author instance. So we're not talking about publics at this time, but on Author it provided a lot of gain. And also it applies to Swift publishing because Swift also needs to update metadata after everything is done. So it's kind of a future-proofed improvement if you want. And then there's also reduced risk of olive memory problems caused by massive publications that, as we see from these slides, triggers massive reindexing. As a freebie, we also get slightly smaller index size, which is always nice. And as a consequence, like eliminating the problem reveals other issues that become more prominent and can become also subject to be tackled as well. And in this case, like after we've recorded pretty much sync low after this optimization has been done, the claim graph changed. And as I said, other problems started to become more visible. So we got more food for thought what to do next. So in this case, that was some customer related code that we also like suddenly got an idea how to improve, and our like also internal operations related to, for example, how we secure the payloads that descend from public to author, and the cryptographic operations that are invoked during that process. And couple of words about what we have used to actually conduct this investigation. In this case, I've used async profiler, which also is something that is currently inbuilt in IntelliJ. So if you just run something at local cost, you can just use it from your IDE, which is very convenient. But in this case, since we were running most of the recordings remotely in the cloud, async profiler comes in very handy. And in the next slide, we will see why. And I wanted to mention that, for example, JProfiler also comes with similar tooling. It was just not as convenient to use in this case as async profiler. And it's very handy because it's CLI based. It's like one executable file that you just drop in wherever your software runs, and then no need to reconfigure your app or anything. You just start it, and it's ready to roll. It's free, and it's open source. There's a link to GitHub. It can measure all sorts of metrics. In this case, we were after CPU, but like wall clock time, executions, memory allocations, etc., also are available to trace. And also it outputs very convenient HTML-based plain graphs, which are very very easy to process and read. And as a consequence, a bit of a shameless plug, I've also written some boilerplate scripts, also using AI heavily, that simplify the process of actually injecting the profiler into running pods in Kubernetes or in Docker containers. And whoever may be interested in actually running it can refer to this repository in our GitLab, where those scripts are, and start using them as well for your own profit. However, this, sir, 3 minutes more. Okay, so there were some other improvements that we have done. So as I mentioned, we have improved this cryptographic operations that are done when author talks to public. So now, besides of RSA, we enable other cryptographic algorithms, and now we're using signature instead of encryption. And on pass with the one channel is already secured with MPLS enable, any no signatures are even needed at all, which also speeds up for that option quite a bit. We have improved also live copy module. So probably most of you know what it is. It's like this heavy duty module that synchronizes potential large content trees, like the master and the actual live copies or slates. And it was always perceived as a small one because of how much stuff it actually is doing. But lately, we had some extreme cases where it was bringing down systems quite a bit. And also, plane graphs helped us troubleshoot this module, and we have revealed that that's where the live copy synchronization is largely dominated by actually Lucene queries, Jakarta queries that are executed. And like, this information give it, like, we have food for thought, like how to improve the performance of the module. And we have implemented the queryless algorithm that premaps master trees to live copy trees, optimize the JSON commit batches, and the synchronization process improved up to 50 times. Of course, like, we're talking about like extreme cases with large trees, but generally that's a huge orders of magnitude improvement and performance there. We have also improved the imaging model, so now there is possibility to control the concurrency. So imaging model will no longer suddenly bring the instance down. A lot of assets are dropped into the system, and variations are generated in parallel. Oh, sorry. There's also subsequent now can be enabled in imaging, which can be very useful when we're dealing with generation of, let's say, thumbnails. So, and I encourage you to go ahead and check out the latest imaging documentation, which describes how it can be enabled. But like with this technique, a lot of RAM and CPU can be saved when small variations are generated with very low sacrifice in quality of those images. And there's been a lot of other, like, maybe also quite significant, maybe small in scale improvements. For example, Magnolia no longer indexes workspaces where index is not needed, like versions. We optimize our own, some of our JSON wrappers, avoiding some sensitive and heavy operations, like, for example, avoiding double session units in the system. We're progressing in improving our delivery APIs in the same vein, which by saving like performance and resources here and there, we have managed to at least internally gain a lot of speed up in how delivery responses are generated. And transitively, also comments we're publishing got additional improvements. So when it will be released, it will be faster than in the beta and alpha versions. And that's pretty much what I wanted to highlight briefly. So I know it's been a lot of content, a lot of information, but those who are interested, I leave the link to an epic in our Gyrant that started it all and has links to other like problems and sub ethics that we have in Takwen, and you can observe the work in progress. And if you want to get in touch, my email is here, so I will be happy to answer questions and maybe collaborate on some other problems. However, I'm on paternity leave for summer, so I might be slow very small. Write that down.
All right, thanks so much, Sasha.